What is symmetry? Sameness, I never heard. Yes, that's true. But how would you give me one word or two words that'll describe it? Symmetry.
Symmetry.
You're using the same word. You can't do that. It's fine, symmetrical. No, you can't use the same word. Yeah, not parallel. That's a mirror image. Or a reflection. If you ever get a chance to go to the mountains in the early morning, take a hiking and go to a lake, they're always perfectly calm. And anything on the other side, you'll see a mirror reflection of it. It's really cool. So it's so relaxing, nice and cool and everything. There are three types. Three types of symmetry. The first one is about the y-axis. This is a horizontal reflection. What that means, if you have a point in the first quadrant, you'll have a mirror image in the same y value and the exact same x value, except the signs are different. So this is what we say about the y-axis. So the points look like this. It goes from xy and it goes to negative xy. Mathematically, we say this. F of x equals y is the same thing as f of negative x equals y. So what's the only thing that changes there?
Yeah.
Yeah. So if you change the sign of the x value, the y value doesn't change. With what we did last time. Give me three functions and their graphs that satisfy this reflection, this symmetry effect. Which functions are symmetric about the y-axis? Now I know, no cheating, no looking back. Try to remember. Yes, the parabola is one of them. Very good. Very good. Very good. So if I had negative X or positive X, they both equal the same Y value. Very good. That's one of them. And what's the next one?
Would it be, it would be like, two lines between X, that was called.
Two lines between X or out?
Outside of it, sorry.
Right. What's that called? The two lines that are on both sides of X. What's that called? Absolute value. What does that graph look like? Two V's. Because it's a linear equation on this side, if it keeps going that way, but you can't have a negative answer, so it bends back up. So it's a V. That's the absolute value. Yes, that's exactly the same thing. One more, and then we'll go to the next one. What's the easiest one to graph? So what's that one? The constant function. Because it's a horizontal line. These are all symmetric about the y-axis. The second type of symmetry is about the x-axis. So if it's symmetric about the x-axis, what stays the same and what changes? Very good. Yes, exactly right. The y's change from positive y to negative y, and the x remains the same. That's a vertical reflection. So x positive y has a mirror point at x negative y. So what this one says is, if I have a function, I put an x in there, I equal y. Or if I put an x in there, I get a negative y. So if you change the sign of the y value, the x value doesn't change. So it's symmetric about the x-axis. Now, the problem with this Is our functions symmetric about the x-axis? ¿Por qué no? Vertical line test, yes, because by definition, if the x value stays the same, it fails the vertical line test. So it's not a function. So would the graphs of this be in the library of functions? No. They could be if, for example, well, we know what this function looks like. It's a parabola. Well, what if we had this? Then it would be half a hyperbola. But because that's not a function, we have to make it a function. How do we make it a function? Well, if we solve for y, what do? You square root both sides. Since you square rooted something that was squared, you have to put a plus or minus in front of the other side. So the square root and the square cancel. So y equals plus or minus square root of x. That's that graph. But the problem is we can't put negatives inside there. So what we do here, we limit our domain from 0 to infinity. So we only look at the positive values. Which is that where it's come from? Right. Well, not exponential. This is the radical. This is the y equals square root of x. No, because we're looking at the x because, well, we don't want to have any positive. We don't have any negatives. The only way we can do that is by limiting. I can only put positive answers there, and then that will affect the range. But yeah, I see what you're saying. Very good observation. But if I restrict the domain to just be positive values, then it means I only want positive first quadrant answers. So there aren't any example functions other than this. Oh, there's another one. Well, there's two more. The circle and the oval. If it's centered at the origin. Because for each one of those, the x's are the same for two different y values. So then again, remember what the formula for a circle looks like at the origin? You have x already.
Y minus k.
Yes.
And squared equals to radius.
Very good. Yes. So at the origin, we have this. X squared plus y squared equals r squared. So basically what this is saying is you have a function that's symmetric about the y-axis if the exponent of y is an even integer. So if the exponent of y is an even integer, then you have a function, or not even a function, and a graph that's symmetric about the x-axis. And the last one is about the origin, which is at 0, 0. What changes here? So let's look at the graph of this one. If I pick an X value and map it to a Y value, then across the origin, I would have to have the same negative X and negative Y value. That's how it's symmetric about the origin. So this is what it looks like. The point XY maps to the point negative X, negative Y. Or more so, f of X equals Y. Very good. Negative X, f of negative X equals negative Y. That's the across the origin, right? But what it's saying here is if you change the sign of X, then the sign of Y changes. There. In general, if you change the sign of either value, then the other changes accordingly. Then the other value changes sign. Awesome. So basically, if it's quadrant 1, then it matches quadrant 3. If it's quadrant 2, then it matches to quadrant 4. So in other words, because all of the examples I have here is positive, positive to negative, negative. No, I could do any combination thereof. I could have f of negative x, y, that goes to x negative y. That's symmetric about the origin as well. Or I should have done it this way. F of negative x equals y equals f of positive x equals negative y. Now, two of them have special names. The first one, if it's symmetric about the y-axis, we say that that is an even function. If it's symmetric about the y-axis, it's an even function. And if you notice, these three examples we have here, if you had to give the absolute value an equation, what would it be? What equation would, if you put a negative in there, it gets rid of the negative and just makes it a positive of that number? The square root of x squared. Think about it. When you square a number, what happens? If it's a negative number, you square it, becomes positive. And when you square root it, it breaks it back down to this. So -2 times -2 is +4. Square root of 4 is, so that's how it works. So now, what do you notice about the x values in these functions for even functions? X squared, no x. So if the equation doesn't have any x's, if it's a constant or an even exponent, then it's an even function. So it only has even exponents and or a constant. It could just be a constant number. Those are even functions. The second one is across the origin. If it's symmetric about the origin, we call that an odd function. Now, let's see why that is. Give me 2 examples of functions that are symmetric about the origin. Yeah, the first one we have this one. Or we have one that's going up. What's the difference? What's this one? What's this lying down one? Yeah, this is cube root. And what's this one? Nope. You notice they're both odd factors. The root is odd, so that's an odd exponent. The exponent is odd, so it's an odd function. Odd functions cannot have a constant number. Why? Why can odd functions not have a constant number in the equation? So if you have an odd function in the equation, there's only negative exponents. I mean, not negative, but odd exponents. 1, 3, 5, 7, 9. There are no even exponents, and there cannot be a constant. What is a constant? What does a constant look like if I change signs of x? It's symmetric about the y-axis. But yeah, and so if it's any part of the constant, that reflects it across the y-axis, and that's not what we want. We want only the x-axis, which makes it easier for us to define. I'm gonna give you some examples here, and you tell me if they're odd, even, or neither. So here's the first one. All right. Let's do the first ones. Odd, even, or neither. Yeah, because even, and the constant. Next one. Even. Because they're both even exponents. How about this one? Because it's only a constant.
Neither. Because I haven't.
Very good. Because these are all odd exponents and it has a constant. It can't have odd exponents cannot have a constant. Number 5. Because that's 7, that's odd. What's this exponent? 1, and that's odd. This one. 8 is even, 5 is odd. You can't mix them up. And the last one.
X.
Yeah, this is odd power,
Oh.
and that's a constant. Yeah, so the reason I showed you that shortcut is because traditionally what you're supposed to do is you're supposed to plug in values. For example, if I gave you this equation, x squared plus 3, how would we test that that's odd, even, or neither? Well, we'd have to do 2 things. Pick a value for x, say 2, and -2, and plug them in there. 2 squared plus 3, 4 plus 3 is 7. -2 squared plus 3, +4 plus 3. So x goes from +x to -x, and the y stays the same. So that's across the y-axis. So it's an even function. Boring. A lot of work. Boring. So it's much easier if you just, because in your homework assignments, you see that as well. Like it says here, test symmetry for respect to the x-axis, y-axis, or the origin. Well, we know the y-axis and the origin. How do you test those? Without doing any math. Yeah. If it's symmetric about the y-axis, it's a what kind of function? It's an even function. So if this is this function even? So that function is symmetric about the y-axis. Is it an odd function? So it can't be around the origin. Now you just have to write, is it symmetric about the x-axis? Well, does the y have an exponent? No, so it's not across the y-axis. The next one. Is it an even function? All the exponents are even. But it's not really a function, but it is even. It's symmetric about the y-axis. Is it symmetric about the x-axis? It's symmetric about the x-axis because the exponent of y is even. Think of the y equals x squared. So x equals y squared goes up and down. Is it symmetric about the origin? No, because if I plug in -x, I can't get a -y. Or can I? If it's origin, okay, let's look at this one. Let's do this one. If it's symmetric at the origin, let's see how we test it. This is example 2. We have x squared plus y squared equals 5. Oh, actually, it's x of, it's y to the fourth, sorry. Yeah, but before I go any further, let's look at this. Is this equation what's the graph of that equation? We just talked about it a second ago. We just talked about it not too long ago. Circle. Remember x minus x squared? So the center's at the origin. What's the radius?
Two.
2, because it equals r squared. So at least you caught it. So a circle. Is it symmetric about the y-axis? Yes. Is it symmetric about the x-axis? Yes. Is it symmetric about the origin? Yes. That's a circle. If I had an oval, is that symmetric about the x-axis? Yes. Is it symmetric about the y-axis? Yes. Is it symmetric about the origin? Yes. Because these over here will map through the over here. Now, why are these not even? Let's pretend we're solving for x. We have x squared equals 5 minus y to the fourth. When we get rid of the square, we have to square root both sides, right? Because x is squared, I gotta put a plus or minus on that other side. So automatically, for any y value put in there, I get a positive negative x value. And the same thing, if I solve for y, I get the same thing. I get a plus or minus this answer. So because of that, it's symmetric about the origin. Because of that, it's symmetric vertically, and because of that, it's symmetric horizontally. This is all three of them. So basically, if all the x's have even exponents, which they do, if all the x's, then it's symmetric about the y-axis. Like same logic. If all the y's have even exponents, then it's symmetric about the x-axis. And if they're both even, then it's symmetric about the origin. All right. I really don't think this should take more than a couple of seconds. It's asking, is it odd, even, or neither? Yep, because that's odd, that's odd, that's odd. No constants. It's an odd function. This one,
Even.
even, and a constant, it's okay. Yeah. No, it's only the x's you're looking at. Because remember, what is the graph of 7? It's a constant. It's a horizontal line. So, and there are no x's on it. Pretty straightforward. So that's it for that section.